glass looks pretty much the same as any other glass, but by this stage of the course you'll realise that we wouldn't be looking at it if there wasn't something special about it. For a start, it's got a mark on it, and when it's filled to this level, it's got exactly half a litre in it, just as a half pint or a 1 pint glass have lines on them indicating when they've the right amount of beer in them. There's more to it than that. We designed this glass just for this programme. It's a special shape, and in the rest of the programme we'll explore that shape. Start from the glass. The easiest way to see where the shape came from is to turn it on its side. Now this shape comes from rotation about the x-axis. It's a volume of revolution, obtained by rotating this area. But where did the area come from? Well, it's the area under this curve, and that's just part of this curve. So now the questions are, what's the function corresponding to this curve, and which bit of it have we used? So our design comes by rotating this part of the curve about the x-axis. Now, what about these dimensions? Here's the widest part of the glass, here's the top of the glass and the mark, and here's the base. We'll be answering these questions later in the programme, but first let's have a look at the curve itself. What is this curve? Well, it's the graph of f of x equals x e to the minus x. And why choose this function rather than any other? Well, we thought of several possible functions and then sketched their graphs, following the same graph sketching techniques you've been using in this block. And we decided that we liked this shape best. So, how did we sketch x e to the minus x?
I'm going to sketch the graph using the steps from Unit 2 of this block. This function is a bit different from those you've met so far, though. It's got this exponential bit in it. Now you know that all exponential functions have graphs which look like this or like this. In every case, the function is always positive. And that tells us something about x e to the minus x. It's 0 only when x is 0. And its sign, too, depends only on x. F of x is negative when x is negative, and positive when it's positive. So the graph crosses the x-axis just once, at x equals 0. Well, that's all I can find out about f of x directly, so now we'll use some calculus. First, let's get f prime of x. X e to the minus x is a product, so f prime of x is the derivative of x, that's 1, times e to the minus x, plus x times the derivative of e to the minus x, which is e to the minus x times minus 1. And tidying that up, I have f prime of x equals 1 minus x e to the minus x. Now what? Well, let's look at the sign of f prime using sign diagrams. First, 1 minus x. That's 0 when x equals 1. If x is less than 1, 1 minus x is positive. And if x is greater than 1, it's negative. Now the other part of f prime is this e to the minus x term. But you've already seen that e to the minus x is positive no matter what the value of x. So combining these two, we get the sign diagram for f prime. 1 minus x times e to the minus x will be positive here up to x equals 1, and negative if x is greater than 1. Right, so now we've got some information about f prime. Next, what about f double prime? If you differentiate f prime in the same way as we did for f, you'll get x minus 2 e to the minus x. And again, let's look at the sign diagram for f double prime. F double prime is negative if x is less than 2, and positive if it's greater than 2. Now, before the program, you filled in these bits of this table. And I can complete it using the sign diagrams. F prime is positive up to x equals 1 and negative thereafter. And f double prime is negative up to x equals 2 and positive thereafter. And now it's just a question of using the table to help sketch the graph. When x is 0, f of x is 0. And f prime of x is 1, so I can draw in this tangent. The next important point is x equals 1. F of x is 0.368. That's about here. F prime is 0, so the tangent is horizontal. And the signs tell me that f prime goes from positive to negative. So x equals 1 must be a maximum. And the last important point is x equals 2. Here's f of x. F prime is minus 0.135, so the tangent is still almost horizontal. And f double prime is 0. The sign of f double prime changes from negative to positive. And that tells me that the curve is concave down here and concave up here. There's a point of inflection at x equals 2. If x is greater than 2, the curve continues to decrease because f prime is negative, but it will never cross the axis again. So now I can sketch the curve. It's negative down here, crosses the axis at the origin, rises to a maximum at x equals 1, crosses the tangent at x equals 2, and then decreases towards the x-axis, getting closer and closer as x gets bigger. So that's how we got the sketch to see what our glass would look like. And we've also answered another of Anne's questions. The widest point of the glass is at x equals 1. And this is 0.368.
So that's how we got this sketch. And the maximum is here at x equals 1, and it's 0.368. The next thing we did was to decide where to put the base of the glass. And so we made an arbitrary decision to have the radius of the base of the glass, this distance, exactly half of this maximum. That is 0.184. But now there's a problem. What value of x makes x e to the minus x 0.184? We want x and know x e to the minus x. That'll give us an equation in x. Let's see what it is. Here's what we know. We know that x e to the minus x is 0.184. Now the first thing to do with this is to get it in the form something equals 0 by rearranging the equation. It's x e to the minus x minus 0.184 equals 0. And how do we solve this? Well, you met one good way of solving equations earlier in the block. It was this, the Newton-Raphson method. Now, this is the rule for any general f of x equals 0. So let's apply it to our special equation. The iteration we want is xn plus 1 equals xn minus this function evaluated at xn divided by its derivative at xn. So the top bit is just xn e to the minus xn minus 0.184, and that's divided by the derivative of this. Well, this bit is a constant, so its derivative is 0. And we've already got the derivative of x e to the minus x. Remember, it's 1 minus x times e to the minus x. And I want it evaluated at xn. So here's the iteration formula for finding x. We'll do it using this micro. Now, if we look back to the sketch, the answer we want is somewhere between 0 and 1. So a reasonable first approximation is halfway between them. So I'll take x1 equals 0.5 and put that into the computer. The result is 0.232 to 3 decimal places after just 5 iterations. But what is this number? It's this distance. Right, so now we've got 3 of our dimensions, but before we can relate them to our glass, we need to decide on the scale. What physical length corresponds to 1 unit on our graph? Well, the easiest dimension to measure here is the height, which is length on the diagram. In experimenting, we discovered that if the height was 15.5 centimetres, the glass would hold just over half a litre, and that would allow us to put the mark just below the top. And interpreting that on the graph means that 1 unit is 10 centimetres. A height of 15.5 centimetres corresponds to 1.55 units along from this point. So this is 0.232 plus 1.55, which gives us 1.782. So these are the dimensions of the glass. In a minute we'll find its volume. That'll involve integration. And it turns out that you have to use integration by parts, twice. So first, let's look at an easier integral that also involves parts, but only once. How would you find the area under this curve? Here's the area we're interested in, between these two x values. Now the function is positive along here, so the integral is the same as the area, and it's this. It's the integral of x e to the minus x between 0.232 and 1.782.
If we want to evaluate this, the first thing is to find a primitive of x e to the minus x. And then we can use the fundamental theorem of calculus to work it out. What method of integration looks the best bet here? Well, this is a product, and this bit of it is a composite. So substitution might work, but there's no easy or obvious connection between the x and the e to the minus x. And that suggests integration by parts is more likely to work. Let's just check that out. Parts involves differentiating one bit of the product, that's f, and integrating the other, that's g prime. If parts does work, then you'd like this bit to be an easier integral than the one you started with. So which of these is f and which is g prime? E to the minus x is a function which can be integrated or differentiated, but it doesn't get any easier. It's always something involving e to the minus x still. What about x? Well, differentiating it gives 1, a constant, and that's easier. So it looks as if x is the best choice for f here. And then g prime of x will be e to the minus x. So f prime of x is 1. Now g is the integral of this, and that's not too bad, it's minus e to the minus x. Now using the parts formula, the integral of fg prime is equal to fg minus the integral f prime g. Two minuses here make a plus. So this is the integral of e to the minus x. But we've just found that e to the minus x was the same as g prime, so this integral is minus e to the minus x again. And tidying all that up gives minus 1 plus x e to the minus x. Now we want the area, so we can now use the fundamental theorem. The area is the difference between the values of this primitive at 1.782 and 0.232. And that turns out to be 0.509 to 3 decimal places.
So the integral is 0.509, and remember, that's an area. But we want the volume of our glass, and we get that by rotating this area about the x-axis. Here's the area. Now, if it's rotated about the x-axis, we end up with a volume. And that volume can be found by taking the limit of the sum of separate disks, each of radius yi and width delta xi. And that limit is given by this integral. It's the integral between a and b of pi y squared dx.
Here's the formula for the volume of revolution about the x-axis for a function y. It's the way you'd find it written down for easy reference, in your handbook, for instance. Now we've got to apply this general formula to our special function by putting x e to the minus x in for y. What integral will we get? Well, it's the integral of pi times this squared dx. Now we can take the pi outside the integral sign, and then this bit becomes x squared e to the minus 2x dx. And this is very like the integral we had for the area. It's something involving x times e to the something. So parts ought to work again. Because if I take x squared as f, f prime will be an easier function. So let's do it. F prime of x is 2x. That leaves g prime of x as e to the minus 2x. So what is g of x? Well, let's try e to the minus 2x. Differentiating that gives us the e to the minus 2x we want times minus 2. So g of x must be minus a half times this. So now we can apply the method. The integral of f g prime is f times g minus the integral f prime times g. This simplifies a bit. The 2's cancel, and there are 2 minuses. So this is just the integral of x e to the minus 2x. And that's even more like our area integral, so we can use parts again. I'm not going to go through that calculation, but if you did it, you'd finally end up with minus a half e to the minus 2x times x squared plus x plus a half. And the volume, what about the volume? Well, that's given by the difference between this at 1.782 and 0.232, except I have to remember to put back in the factor of pi that I left out here. And on my calculator, this gave me minus 0.243 minus 0.776, which turns out to be 0.533. And that's to 3 decimal places. But 0.533 of what? Well, earlier in the program, Anne explained how we chose our unit of measurement as 10 centimeters. So a square unit is 10 by 10, that's 10 squared, or 100 square centimeters, and a cubic unit is 10 cubed, or 1,000 cubic centimeters. And 1,000 cc's is just a litre. So this volume is 0.533 of a litre, just over half a litre, as we wanted.
Now the mark on this glass shows when the volume is exactly half a litre. So the final question in specifying our design is, where should the mark come? What we want to know is the value of x here, and then we'll know how high up the glass the mark should be made. And we've now got enough information to be able to work that out. Let's call this value b. What do we know? Well, the volume from here to here has to be half a litre, 0.5. And we also know how to find volumes by integrating. So we want this to be 0.5. In other words, the difference between the values of the primitive of this at b and 0.232 is 0.5. But Mike found a primitive for this earlier in the program, which gives this equation. Here's the value at b, and this is the value at 0.232. And this just tells us that b is one solution of this equation in x. Here we've got the variable x instead of the solution b, and the two constant terms have been combined to give this. To find where the mark is, all we have to do is to find a solution of this equation. It's rather a nasty looking one, but you'll see that there's a quadratic factor here multiplied by this exponential. And we can use Newton-Raphson again, provided we start off with a reasonable first approximation. We've asked you to do that after the program. And then you'll have the complete specification of the glass.
The mark looks as if it's about a centimetre from the top. Let's check that it really does give a volume of half a litre. The best way I know is to share a litre between two glasses. And to see if it really does come up to the mark.